Okay, we're going to do some algebra with functions today. And basically, we have some operations that we're going to do. We've worked with functions, different types up to this point, polynomials mainly. But we can do different things. And here's some notation. We can add functions. So we might have f of x plus g of x. Another way to notate that is like this, f plus g of x, like that. So, I mean, I don't know which one is really simpler to write. They're both about the same amount of writing. So I prefer this one, but I mean, I like this one, but this we can use also. Okay, so that's addition. We can also subtract. We can have f of x minus g of x, and that's denoted this way. Okay, now when people really get lazy, they just do this. And this one, f minus g. Once you get higher into math, people seem to get lazier and lazier. So they just write this with the understanding that we're talking about functions, right? Okay, so we can also multiply. We can take two functions and multiply them together, like that. And then that notation looks like this. F times g of x, like that. Okay, and again, some people might just write it like this, with the f and the g right next to each other. Okay, you can also divide f of x over g of x. And you probably already realize that it looks like this. Okay, all right, so let's do an example. Let's say that f of x is equal to, let's say x squared minus 3x plus 5. And g of x might be x to the third minus 2x squared plus 7. So let's see what kinds of things we can form here. Let's go for the f plus g of x. Well, that will just be x squared minus 3x plus 5, and plus an x cubed minus 2x squared plus 7. If you can simplify, you do so. So I will. This will be a minus x squared minus 3x and then plus 12. That's it. Okay, we can also find the difference between these two functions. Okay, that will just be x squared minus 3x plus 5 minus, now here's where you have to be careful because you're going to subtract this whole function, and I would advise using the parentheses around it. That way you don't make any mistakes on the signs. So watch the signs on this. That'll be a plus 2x squared and a minus 7. So this gives us a negative x to the third, and then we got x squared and 2x squared is a 3x squared minus 3x and then minus 2. Okay, let's see, let's do another operation. Let's do the multiplication. F. You know what? That's going to be a long problem, so let's just let's take another example with a couple different functions. Let's find f over g when f of x equals, let's say, x to the third minus 3x squared plus a 1, and g of x is equal to, let's just say, x squared minus 5. Now, we'll form this quotient function, f over g. We'll just take it like this now. So this is f over g. We'll take the x cubed minus 3x squared plus a 1, and you'll just literally put the other function underneath it. Now, if there is a way to simplify, we will, but we're not going to go into long division unless it serves some other function for us. No reason to do that. If there's an obvious simplification, you make it. you're not going to spend all day trying to simplify these. Now, something about the domain on these. Well, we didn't find a product yet. Let's take another example. Let's say we're given that f of x equals square root of x, and g of x is x, we'll say square root of x minus 5. And then let's go ahead and find f times g of x. Well, that'll be root x times root x minus 5. So we'll write that as root x minus 5 root x, which we can write as just an x squared minus 5 root x. Now, this simplification right here assumes when we go from see this in here, right there, we're multiplying those two together. We're assuming that we're working with real numbers here, okay? We're not going to be working with imaginaries and doing these operations. So assuming these are, x is greater than 0 here and here, okay? And then that would give us this. Oops. Let's undo that. Come on. Undo that. Yeah, that's just an x minus 5 root x. And again, that assumes that x is positive, which it most likely is because you couldn't have imaginaries in here. So, all right, now just another mention up here. The domains now of these new functions can be different from the originals. Notice the original two functions, the implied domain is all reals. Okay, when you look at these individuals, f and g, there's no restrictions on x. But when you throw this in here, we have to make sure that the denominator is not 0. So we would have to have, for our domain for this one, we would have to have x squared minus 5 never equal to 0. So that would be that x could not be equal to plus or minus root 5. So that would be our domain. So this, another way to say that is just x is real, not equal to plus or minus root 5. That would be your domain. Okay? So you got to watch out for things like that when you're constructing new functions like this. Typically, those are the ones that you worry about. Now, when you form functions like these, the domains are the intersections of the domains of the original functions that you're working with. So you just have to find the intersections, whatever they are. Mostly that's all real numbers, but it could be different depending on what's given. Okay, so that is what we do. There is one more type of function that we're going to talk about. I'm going to add a page to this. Oh, by the way, just go back to that. That last. These functions that we just talked about, we did the addition, subtraction, multiplication, division. And the examples that I worked with, I was using two different functions, but you can also, you can form f plus f like that. I mean, you don't have to have a new function. Now, of course, if you took f minus f, I mean, that will be something, it'll be a 0, okay? Because there's nothing left that you subtract something from itself. But it is a function. It would be a new function, and it'd be a 0. Likewise, you could take f times f, like that. Okay, so you can square a function, make a new function out of it. Now, if you divide the function by itself, like that, of course, you're going to get a 1. If you divide anything by itself, it's a 1. So you have a new function, which is a 1. Okay, so I just wanted to say you can do this. And you could find things like g times f times another, let's say x, and then you can multiply that by another g. g of x times that. I mean, there's no limit to the algebra that you can perform now with these operations. Lots of different things you can construct. Okay, now let's go back and look at our next topic, and that is a different kind of thing called a composition. Composition. Okay, and that is composition of functions. So maybe a new idea for some of you. This is the notation that we use. So there's a little circle in there. It's not a dot, it's a little circle. And this is read as this. F composed with G. F composed with G. You could also do it this way. This would be G composed with F. Okay. F composed with G. And there's a difference because what this actually means is this. It means F of G of X, like that. And this one means G of F of X. Now this is not, in general, it's not a commutative operation. You can't just switch F with G like that. Like addition is commutative. F plus G is the same as G plus F, right? F plus G is G plus F. But when you do this composition, it's not the same, okay? You won't always get the same functional result. What the answer that you're going to have is not going to be different. So in general, these will not be the same as each other. Not usually the same. Okay, not usually equal. All right, let's take an example then. Let's say we have f of x is, let's say it's x squared, and g of x is maybe the square root of x minus 5, for example. And let's just say we want to find f composed with g, like that. Well, that would be f of g of x. So when you have your f over here, you're going to replace the x with a g, and you're going to square it, because that's what f does. It takes an input and it squares it. Whatever the input is, this is what it's going to do to it. It's going to square it. Okay, so our input is g itself, a function. That's okay. We can input functions inside of functions. This would become an x minus 5, assuming again that x was larger than 5, and we would assume that that would be true from here. If x was greater than or equal to 5, wouldn't make any sense otherwise. Okay, so that is a composition. We just formed our first composition. Okay, now we could also have said to find g of f of x, or g of f and x, some people would say. This one would be g of f of x, like that. And that would start with your, starting with your g, we would have this f of x stuck in here minus the 5. So you're taking the g function and you're putting inside of it, instead of an x minus 5, you want f of x minus 5. Well, we do that first, and then we can put in the function f of x, so it becomes this. Okay, so that's our new function now. And of course, when we talk about the domain for this new function, even though this, I'm going to go back to this one here, even though you can see this function as it stands, let's call it h of x, give it a name. it looks like it has all real numbers as its domain, but we know that because of where it came from, because of this, that there were certain restrictions that still have to be in place. We still have to hold them. And that one restriction was this over here, that x had to be greater than or equal to 5. So that's still true over here. Okay, you still want x to be greater than or equal to 5. Okay, only. Even though it doesn't look like that's one of the restrictions. Okay, we wouldn't, because we need to be able to work with this form of the function as well as this one. This is where it came from. Okay, so we couldn't be using input values for our function here for f that were outside of range values that were in here, basically. Okay, anyway, let's continue. Now this one down here, this function wouldn't make any sense unless this were greater than or equal to 0. So that implies a certain thing about x here. So x has to be greater than root 5 according to this, and also x could be less than greater than or equal, less than or equal to root 5, minus root 5. Okay, so so this will be true as long as those are non-zero. So you'd have to have that, and that would be true if this were true, or if this were true. Okay, so this is kind of a split domain now for that. We'd have to watch out for that sort of thing. But all right, so that's good enough for now. Let's see, what else can we do? We can also find, let's say we had to find f of x. I mean, you could do that. So what we're talking about in this case, x squared and root x minus 5. Let's go. Okay, so we got to take an x squared. In other words, f of x, like that, which is, you're going to take f of x squared. Well, that means you're going to square it also. So you're going to have x squared, which is x to the fourth. Okay, x to the fourth. So that's your new function. You did that. What else can we do here? All right, well, okay, that's probably good for now. Okay, one more thing, that is what makes these useful and later on useful is to be able to view a function. Let's say I have a function h of x. Let's say it's equal to, let's say x squared plus a 1 . Okay, x squared plus a 1. And you're asked to say, how could this be a composition of two functions? Okay, how might this be a composition of two functions? Now, these are not unique. These, what you view this as, they're not unique. So you could say, hey, what if f of x were equal to the square root of x? Okay, in fact, you know what, let's make it even simpler than that. let's just make it f of x equals x. And let's say g of x is equal to, well, let's make it x squared. I'll stay with that. And let's let g of x be x plus 1. Then we can see that one way to view this, view h, we can say, well, h must be g of f. It's a composition, since this would be g of x squared, which when we place it into g, notice when you place that into g, you would be taking, instead of an x, you have an x squared plus a 1. So this would be a way to view this function. It could be considered a composition of these two functions here, in the sense that h could be viewed as g of f of x, like that. Okay, so okay, so let's see. That was all I needed to. That's all I wanted to say about that one. Let's take another one of those. Example. Let's say h of x is equal to square root of x squared minus 5. Okay. No, you know what? That's too obvious. We already kind of worked with that one. So let's make it the third root of 2x plus 1. Okay. So now remember, these are not unique, but let's come up with a composition now of two functions. Okay. Let's keep it simple. Let's make g of x equal to cube root of x, and f of x be equal to 2x plus 1. Then you can see that h is actually g of f, since it's pretty obvious that if you take the cube root, that's g evaluated at f of x, you get this cube root of 2x plus 1. So that's one way to view it. Sometimes you can have compositions of compositions. So somebody else might say, hey, you know what? Well, that's fine, but what if I had a third function involved here? Let's say I had u of x equal to x plus 1. And let's say I had f of x equal to 2x. And let's say I had g of x equal to that cube root of x, like that. Then somebody might say, well, this was sort of a composition of a composition. You could say f, well, okay, I want the h, so I want h of x could be viewed as, first of all, g of u, okay? Because that would produce this. It would be the cube root of x plus 1. And then, see, this shouldn't be h. I'll make this big H, okay? And then, because the idea is that then we can do one more, we can say h of x is actually big H composed with f, like that. Because now when we take this, we're going to put f of x in place here. Okay, so when I take h of x, I put f of x in there. And then that f of x is that just the 2x here. So it just becomes the cube root of 2x plus 1. So there's lots of ways that you can view these compositions as built upon or from each other as inputs. Okay, now we don't typically, I don't think I've ever seen notation with like this, although I'm not saying it doesn't exist. It may, things like this. I mean, you just do them in order from right to left. Okay, this is the same as this, composed with that. Or is it? See, that's a notational thing. We're not going to talk about that right now. There might be a standard for this, but to remove confusion, all you'd have to do is say, if you wanted to compose something, you'd have to build it like this, for example. If you wanted that order to be preserved, you can do it this way. So this takes f of x, takes g, composes with f, and then that result is composed with the h. Okay, h composed with this inside, whatever this is. So they're nested compositions, is what this is. And that's what we actually constructed up here. We have a nested composition that could be viewed as, let's see, I took the original g, I took g of, and I took the u of f, that. So, and u, I replaced f, okay, and x squared, and then that I put into g. So it could be viewed like that. Anyway, so you have some fun with those. And you can compose functions. I think I did one of those in there. Compose a function with itself, f of f, whoops, f of f, like that. Okay, you can compose a function with itself, which in my case here would be 2 times f of x, right? Which is 2 times 2x. So it would actually be a 4x. Okay, that's using this function here to construct this. So you can compose functions with themselves. Okay, anything that you can come up with here. Let me do this one, g of x. And that would be function g, the cube root of g of x, which is the cube root of the cube root of x. Okay, and that's a strange looking function. If you went into the fractional exponents, you'd see something like this, which is x to the 1/9th root of x, like that. Okay. So there it is. So you can do all kinds of different compositions with those. Okay, so that's, now actually one more thing before I stop this. You can do evaluations. If somebody said, okay, here's f of x, and here's g of x. And they said, find f of g of 3. What does that mean? Well, it means this. It's f of g of 3. So what we have to find is g of 3 first, and then use that as input for the function f. So you can do that in stages, or you can do it all at once. For let's in the marginal there. Let's first of all find g of 3. It's square root of 3 from this function. So then here we're going to find f of root 3, which from our function we see is going to be root 3 squared minus 2 root 3 plus a 1. So simplify as much as you can, and that's the end. Okay, so we're able to do that in stages. Okay, you compute this first, and then you find that. You find this first, and then you put that into the other function here. Okay, compute that. So that's how we handle it. If you're only going to do one value like this, then it pays to just do the problem like this. If you have several values to compute, then I would recommend, like if I didn't just have this, if I had maybe several of these, like 3 and 4, 5, 0, and -1, whatever it might be. It couldn't be a -1, by the way, because you couldn't have a negative here. But you might want to find the function in general, the function itself, the composition, and then do your work, because it might turn out to be easier. So if I was going to do that, I would have to take that root x, square it, minus 2 root x, add 1, which is just x, minus 2 root x, plus a 1. So then, if that were considered this h of x, then that's my new function. Then I can compute anything I want. I can compute the 3, which would be 3 minus 2 root 3 plus 1, which we saw that was 4 minus 2 root 3. We could also compute h of, let's say, 4. That would be 4 minus 2 root 4 plus a 1, which is 5 minus 4 is a 1. Or you could, how about 0? H of 0 is 0 minus 2 times 0 plus a 1. That's a 1 also. Okay. H of, notice I'm not using negatives, because I'm not really allowed to use them because of this here. Okay. So okay, so we have a 9 minus 2 root 9 plus a 1. So 9 minus 2 times 3 plus a 1. 10 minus 6 is 4. Okay, so you can notice it's probably easier to do it like this if you have several, because I just keep working off of this function right here, instead of computing in smaller steps. So sometimes that makes it go a little bit faster. All right. So that's all we have there.